Okay, so for today, we'll have our last lecture for this term, which is your moment of inertia. It is also the last topic on your syllabus. So as usual, we'll have a bit of an introduction. So first of all, okay, many engineering formulas involve the use of a mathematical expression in the form of integral of rho squared dA, where rho is the distance of an area or an element to a reference axis, and dA is your differential area. Okay, so recall your integral calculus. Now, this expression appears a lot of times, and therefore, it is now given a name, and that name is your moment of inertia. Now, when we say moment of inertia, it can mean one of two things. It can mean your area moment of inertia or your mass moment of inertia. Now, unfortunately, whenever books say moment of inertia, it is not really specified which of the two we're talking about. However, our discussion will mean area moment of inertia. Okay? So let's see the definition of your area moment of inertia. So it is the measure of resistance of body to bending. So that is your application of this expression when it comes to the equations involving structures or structures of rigid bodies. Okay, so used to measure the resistance of body to bending. Another thing is this expression is used for flexure formulas for beam stresses. And one important definition of this is that it's also known as your second moment of area. Why? Because each differential area multiplied by its moment arm gives the moment of area. When multiplied a second time by its moment arm, it gives the moment of inertia. So to explain, let me show what happens. Okay. The moment of inertia. So we have another term here that's familiar to us here, moment. Recall, moment is just the property times distance. So what we know about moment is your moment of force. So let's denote that as MF for moment of force. And we know that to be FD, right? Now for moment of area, instead of using force, okay, we're going to use area from the name itself. So instead of force, it's area times distance. Now sometimes this area is not uniform. So instead of using A, okay, we're going to use a differential area. So your dA. And then this distance will now be noted as your rho. Okay? So as I said earlier, rho is your perpendicular distance to a reference axis. So same thing here with your FD. Now knowing that, we can create an equation for the first moment of area. So first moment of area. And that is your dA rho. However, to get the summation or the total moment of an irregular shape, we're going to take the summation of this. And recall from your calculus, specifically integral calculus, whenever you have a differential area, to take the summation of that, you take the integral. So this becomes integral of dA rho, or the proper way to write this is rho dA. Okay? So that's the first moment of area. Then, when we multiply this expression by another moment arm, okay, by the way, remember perpendicular distance to a reference axis is also known as your moment arm. So your rho is a moment arm here. And then multiplying this expression by another moment arm, you get your second moment of area. And that is your, multiplying this by rho, you have rho squared dA. Okay? Multiplied by rho, you get okay. So integral of rho squared dA. And this expression, as I've stated in the first slide, is your moment of inertia. So that is also your moment of inertia. Integral of rho squared dA. So don't get confused whenever you encounter the term moment of inertia and it's speaking about a different thing. Or when you encounter the term second moment of area, that is also equal to the moment of inertia when it comes to area. Okay? So that is your area moment of inertia. Another definition of, or another use of moment of inertia is for mass, and we call that mass moment of inertia. So basically, it's a measure of resistance of body to angular acceleration. So one obvious difference of area moment and mass moment is that area moment of inertia measures resistance to bending. Mass moment of inertia measures resistance to angular acceleration. Now, another difference between the two is that area moment of inertia is used in strength of materials, your MEC 32, okay? While your mass moment of inertia will be used in your dynamics of rigid bodies, which is your MEC 31. So I will focus on area moment of inertia because MEC 30 is sort of like an introduction to your strength of materials, MEC 32. So that's why this is what is important to us. Okay, this is in dynamics, this is in strength. Right. So that is the difference. Now, these are our equations. So once again, moment of inertia is denoted by your capital I, and it's equal to rho squared dA. Now, rho is your perpendicular distance from your reference axis. And similar to your force, moment of a force, you can divide that into components. However, here, instead of taking moment of inertia, we say moment of inertia about a specific axis. Now, usually it's about the x or y axis. So that's why this means moment of inertia about the x-axis. And the equation of that is integral of y squared dA, because, for example, in this figure, this is an irregular shape taking a differential area. A differential area is a very small area. Okay? This perpendicular distance to the x-axis is this length right here, and that is just your distance y. Okay, that's why the equation is integral of y squared dA. Likewise, for moment of inertia about the y-axis, your IY, it's about this axis. So once again, you're going to take your differential area and take the perpendicular distance to that axis. And that distance is just your x coordinate. So that's why this is equal to integral of x squared dA. Okay? That's moment of inertia. A topic under moment of inertia is your polar moment of inertia. Now, what is this? What's the difference between your area and mass moment of inertia? Well, polar moment of inertia is under area moment of inertia. So we've talked about getting the moment of inertia of a differential quantity or differential area about a specific axis. Now, it is possible to get the moment of inertia of a quantity for dA about the pole O or Z axis. So the only difference here is instead of taking it from the x or y axis, we're taking it from the pole, or what we call your Z axis. So this is referred to now as your polar moment of inertia. So to be more specific, the definition for polar moment of inertia, it is the moment of inertia for an area relative to a line or axis perpendicular to the plane of the area. Now, it was like to similar to your area moment and mass moment, polar moment is a measure of resistance of body to torsion. So earlier we have resistance to bending, for area moment, mass moment to angular acceleration, and then for polar moment, this quantity is used to get the resistance to torsion, or what we call your twisting about a given axis due to an applied torque. And once again, let's discuss what is polar moment of inertia. So to better understand, let me give you a drawing. So polar moment of inertia. Okay. So by definition, it is moment of inertia about a line that is perpendicular to your plane of area. So let's now draw this in 3D because we're talking about 3D here. Okay, so this is your y-axis. Let's call this your x-axis, and then let's call this your z-axis. Okay. Now our area, our plane area, is on the xy axis, so it's in here. So let's draw an irregular shape there. And then our regular equation, taking a differential area, again. And then this will be your distance y. Okay. And then likewise, this is your distance x. Okay. So that is for moment of inertia. Polar moment of inertia is now taking the perpendicular distance to your pole. This is your pole O. The reason why it's called pole O is because it's passing through your origin of your axis. So pole O. Or also, it's also called the z-axis. So taking the perpendicular distance of that, it's this, right? That. And let's call that distance r. And we call it r because it's actually the hypotenuse of a right triangle formed by your x and y distances from the same differential area. Okay? You can see this is the height of your triangle, and then this is the base of your triangle, which is also equal to x. Now, from that figure, we can create our equation for polar moment of inertia. Okay? So again, it is area multiplied by perpendicular distance to pole O, or once again z-axis, and that's equal to r. And based on this drawing, that's just the hypotenuse. So r squared equals x squared plus y squared, our Pythagorean theorem. And then now, getting the equation of this, let's look at our next slide. The equation there is given by j is now equal to integral of r squared dA. Okay, so it's similar to your moment of inertia equation, or x and y. But once again, here instead of x and y, we use r, or sometimes rho. So how did this equation become this? Okay, so let's use equation I, moment of inertia about pole O or Z. Okay, so O or Z mean the same thing. So let's say Z. And this moment of inertia about Z is your polar moment of inertia. So instead of writing that, we'll write J sub O. Okay, and then equals integral of r squared dA. Subbing r squared from this equation, okay, instead of r squared, we write x squared plus y squared dA. Separating our terms, this becomes integral of x squared dA plus integral of y squared dA. And we know integral of x squared dA is your moment of inertia about the y-axis, and then your y squared dA is your moment of inertia about the x-axis. So this becomes moment of inertia about y-axis plus moment of inertia about x-axis. So J sub O is now equal to Ix plus Iy. Okay, so that's how that equation came to be. Next, radius of gyration. So what is radius of gyration? It is the uniform distance from the reference axis at which an entire area may be assumed to be distributed. It is used to compare how various structural shapes will behave under compression along an axis. And then here it is used to predict buckling in a compression member or beam. Once again, radius of gyration is just a term used in our equation for strength of materials. All of these, your J, your I, are used in strength of materials. Okay, one is to measure resistance to bending, one is used to measure resistance to angular acceleration. The other is here, it's used for resistance to torsion. And then finally, your radius of gyration is a variable used in the formula for predicting buckling for a compression member or beam. So in case you don't know, buckling is when you have a column under supports, and then buckling is when it turns into this. Okay, that's buckling. So let's talk about radius of gyration. What is it talking about? Okay. So once again, let's say you have an irregular shape, your area, right? And this is your x-axis. So radius of gyration is from this term radius. It's the distance from the x-axis, wherein this entire shape may be stretched or rather distributed. Okay. So this shape becomes this. Okay. This shape. Very thin strip. And then this is your length K. And then these two shapes have the same moment of inertia. That is your radius of gyration. Now this is for area moment of inertia. For mass moment now, instead of distributing your area about a strip, you will distribute mass to a point. Okay. So for that definition, it is the distance we're in. That point will have the same moment of inertia as if it were stretched out. Okay. So that's your radius of gyration. And then for equations. So the basic equation for radius of gyration is square root of I over A. And our symbol for that is K. Okay, so now we have your I, moment of inertia, J, polar moment of inertia, and K, radius of gyration. So square root of I over A, and similar to your moment of inertia, it is about either an X or Y axis. So for X, it's square root of moment of inertia about the X axis over A, and then KY is just square root of IY over A. And then lastly, we also have your Z axis or your pole O. So we have K sub O, and that is just equal to integral of J sub O over A. So you have several equations for K depending on which axis we're referring to. Once again, X, Y, and Z axis. Okay, so those are our equations. Now let's talk about a theorem that is used for moment of inertia, which is your parallel axis theorem for an area. Okay. So the parallel axis theorem can be used to find the moment of inertia of an area about any axis that is parallel to an axis passing through the centroid and about which the moment of inertia is known. And then these are our equations. So let's derive again. How did we get this? Okay. So taking this figure, let's try getting that. Let me just copy that figure. Okay. Yeah. Okay. Parallel axis theorem. So we have again the shape. And then this is your reference axis. And then we've discussed centroid in our past lecture, right? So if you take an axis about the centroid, that is your centroidal axis. So it's denoted by your x prime and y prime. It's these two right here, and this is your centroid. So now, parallel axis theorem dictates that if you know the moment of inertia of your shape about its centroid or centroidal axis, you can use that and take the moment of inertia about any other parallel axis. So a parallel axis to this is this axis right here. Okay? So the equation goes like this. So you take your differential area here, A. So let's write our equation. We'll always start with our basic equation, rho squared dA. And then let's start with Ix, since Ix, or moment of inertia about the x-axis, is the more common one to be solved. So again, we're focusing on moment of inertia about the x-axis. And basic equation for that is rho squared dA, or y squared dA. Now, y is the distance of your differential area to your reference axis. Once again, our reference axis is these. Okay? So total area, or rather total distance, is this, right? And that is equal to y prime, okay? This is denoted as y prime, your distance of element to the centroidal axis, plus whatever this distance is. And this distance is denoted by distance y, okay? This is not differential y, okay? That's distance y. Distance of your centroidal axis to your reference axis. So taking the summation of that, okay, rho is now once again this y prime plus this length dy, okay, squared dA. And now you just solve for the integral. This becomes y squared plus 2y prime dy plus distance y squared. Once again, this is not differential, this is distance. Then multiplied by differential area A. I know it's a bit confusing, the symbols that is used in the derivation. Yeah, but again, I just reiterate, this is distance, this is differential. And then let's solve. Let's separate all the terms. So integral of y squared dA plus integral of, or twice the integral of y prime dy, and then plus integral of dy squared dA. Okay? This is y prime squared. Y prime squared. Okay. So now let's look at each term. Integral of y prime squared dA, or simply put, integral of y squared dA is just an equation for moment of inertia, right? And this y prime is distance to the centroidal axis. Therefore, this is just, or this term just signifies moment of inertia about the centroidal axis. And then we have a symbol for that. It's your I bar. And then about your axis x. Okay? So once again, moment of inertia about a centroidal axis, either that's x or y, is denoted by your I bar. Okay? So I bar, then x, since we're talking about the x-axis here. Now what about this? Integral of y prime dy. Well, integral of y dy, this dA, times dA. So in the integral of y prime dA, as you can see, that is just area multiplied by distance to the axis. And we have a term for that. If you recall, that is our first moment of area, right? Integral of rho dA, integral of y dA. So that's your first moment of area. And then, to be more specific, this is the first moment of area about the centroid. Okay, since y prime is from the centroidal axis. So about the centroid. And then looking closely, okay, this is your area, this is your centroid. If this is the centroid, that means this axis divides your area into two equal areas. Okay, even though it doesn't look the same, it's still equivalent to two equal areas. So this area is equal to this area. Now, if you take the summation of y times dA, okay, where y is positive if it's above the x-axis, and then it is negative if it is below the x-axis. So imagining that, if you take the summation of all of that, okay, this plus this, your differential areas here, okay, this is positive, this is negative, it all comes out to 0. Okay, once again, the reason why it's 0 is because area above equals area below, if we're talking about a centroidal axis. And then distance above is positive, distance below is negative. So summation of positive and negative, and then if they're equal, that is 0. Okay? Therefore, this is 0. Okay? Also, first moment of area is not always equal to 0. It's only equal to 0 if it's about the centroidal axis. Okay? So this is important. So 0. So plus 0, and then plus integral of dy squared dA. dy is actually consistent, right, or constant. The distance of your x-axis, or the distance between your x-axis and your centroidal x-axis is the same, no matter where you take your differential area, right? This distance is the same. So therefore, that's constant. So I can just factor that out. This becomes integral of dy squared dA. And then recall, integral of dA is just equal to a. Okay, so from your integral calculus. So therefore, this equals a times dy squared. Okay. And then finally, our moment of inertia about your reference axis is equal to your moment of inertia about your centroidal axis plus area, total area of your figure, times distance of your centroidal axis to your reference axis squared. So dy squared. Okay. So that is for the x-axis. The equation for the y-axis is the same. It's just about y. Okay. There, that's your parallel axis theorem. Oh, by the way, before we move on, I'd like to ask, do you have any questions for moment of inertia up to radius of gyration? Please answer in the chat. Tina? Right. Since none. Do you have any questions for your parallel axis theorem? How about the others? Please answer. Do you have any questions for your parallel axis theorem? Okay. Then once again, so we had our equation for both. Let me go back. Parallel axis theorem. So moment of inertia about the x-axis, your I sub x is just I sub x bar plus a dy squared, and then iy is equal to I sub y bar plus ABX squared, and then J, which is your polar moment of inertia about your x-axis, z-axis, or pole O, is equal to, and polar moment of inertia about the centroidal O-axis plus a B squared. Okay. And then, once again, your Ix and Iy bar are moment of inertia about the centroidal axis. Now, in the same manner, the transfer formula, we call this your transfer formula for polar moment of inertia and the radii of gyration are respectively. So same thing, J equals J bar plus AB squared, and then K squared equals K squared bar plus D squared. It's almost the same. Okay. So that's it for the concept for our topic for today, moment of inertia. Let's now move to examples. Let's begin. Ready your calculators as well. I'm gonna answer number 1 on my own, but you can still follow along. And then we'll begin recitation with example number 2 onwards. Okay, example number 1. Determine the moment of inertia for the rectangular area shown in the figure with respect to letter A, the centroidal x-axis, denoted by your x prime, the axis B, or xb rather, okay, here at the base, passing through the base of the rectangle, and C, the pole or z prime axis, perpendicular to the xy plane and passing through the centroid C. So we're looking for 3 things. Moment of inertia about your centroidal x, your base x, and your polar axis. Okay, let's solve. Okay, example. Okay, let me just copy again the figure. Let's do this. Okay. So let's start with letter A. Moment of inertia about the centroidal axis. This is your centroidal axis. And then to get moment of inertia, recall our equation, integral of y squared dA. However, this is about the centroid, so we'll just change the symbols a bit. So instead of Ix, we have Ix bar for the centroid, and then equals integral of, now instead of y, we'll use y prime. Okay, y prime to denote distance of your area to your centroidal x-axis, and then dA. Okay, so now the problem here is to solve for y, and then your dA. So y is just this distance. Okay, so the next step is to select your differential area. Okay, so differential area, as you can see in the figure, it can be a rectangle. So usually, you want to select your area or your strip, in this case, parallel to the axis in question. The axis in question is your centroidal x-axis. So we need an element that is horizontal as well. So that is where this drawing comes in. Okay? So this is a differential area, a differential strip, and we call that your dy prime, okay, or just dy. So therefore, taking the area of this is just dy, height, multiplied by base, and base is constant at this length, which is equal to b. Right? B over 2 plus b over 2, that's b. So therefore, I can rewrite this equation to integral of y prime times dA. Again, area is equal to base times height of this rectangle. Base is b, and then height of this is your dy. Okay? Again, this is all from your integral calculus. B dy prime And then remember, we take our limits. Since we're using a horizontal strip, we need the limits about the y-axis. Okay. So we take this as the center of our axis, so that is your point O. Therefore, this strip moves from this point to this point. So now we need to know the coordinate of this point, okay, your base. If this is 0, total height of your rectangle is h. Therefore, this point is negative h over 2. So this is negative from negative h over 2. And then similarly, to upper limit, this point, that is your positive h over 2. Okay. So now let's solve. As you can see here, y prime b dy. Let's look for what's constant because all our constant terms can just be factored out of your integral. So can anybody tell me what's constant here? Your y prime, b, or dy prime? Constant meaning doesn't change no matter where you put your element or your differential area. Once again, what's the constant variable there? Correct, Carla and Angela, it's B. So that is Ibarra. By the way, this is also your last day for recitation. So for those who still don't have points, I urge you to recite. Correct, it's B. Because as you can see, no matter where you put this element, up or down, the base remains the same, B. So I can factor out B. Okay. And then we're left with y prime, by prime. From negative h over 2 to h over 2. Integral of y dy, that's just y squared over 2. Squared. Equation is squared. Y squared dA. This is squared. Y prime squared. Okay. Once again, integral of y squared dy is d cubed over 3. So b times y cubed over 3. So y prime cubed over 3. And then evaluate from negative h over 2 to h over 2. And once again, from your integral calculus, whenever we have your limits here, your negative a to a, depending on whether it's an even or odd function, I can rewrite this as 2 times b, and then factoring out 3 here. Then we're left with y cubed. And then instead of negative h over 2, this becomes this becomes 0 to h over 2. So in short, instead of integrating from this point to this point, since it's symmetrical, I can just start from your center upward and then multiply this by 2. So that's what happened here. So multiplied by 2, and instead of negative to positive, it's from 0 to your positive. Okay. And then solving for this, you have 2b over 3. Okay. Subbing in your upper limit, this becomes h over 2 cubed. And then minus subbing in 0, so that's just 0. And then finally, okay, this becomes 2b over 3 multiplied by h cubed over 8. So our final equation would be okay. So 2 divided by 8, 4 times 3, 12. Correct, John, it's bh cubed over 12. Okay, bh cubed over 12. So that's your answer for letter A. Right? Next, letter B. Letter B is moment of inertia about your base or about this axis. So letter B. So now we know moment of inertia about the centroid. X sub B is parallel to this. Therefore, I can use your parallel axis theorem. And parallel axis theorem is just Ix Okay, meaning about this axis is just equal to your moment of inertia about the centroidal axis, Ix bar, plus a b sub y squared. Okay, this is just bh cubed over 12. So bh cubed over 12 plus area. Area of this rectangle is just base times height. So b times h. And then distance y squared. So that is distance of your reference axis to your centroidal axis. So it's this length, which is also equal to h over 2. Okay? And then this becomes bh cubed over 12 plus squared. b, h times h squared, that's also h cubed. Then 2 raised to 2, that is 4. Multiplying both of these by 3, okay, bh cubed over 12 equals 3 bh cubed over 12. Okay? Again, multiplying numerator and denominator by 3 so that they have the same denominator. So I can just add them. So bh cubed plus 3 bh cubed, that's just 4 bh cubed over 12. And then simplifying, our final answer would be Ix equals, okay, cancel this out, bh cubed over 3. So this is our equation for a rectangle, moment of inertia of a rectangle about its base. Okay. And then finally, letter C. C, moment of inertia about your pole or z-axis perpendicular to the xy plane. So it's your z-axis. So about there. So z prime. Let's call that z prime. So to solve for that, let's take our equation again for j. Okay. Since this is about the centroid, we'll get j sub o bar. Right? Equals I sub x bar plus I sub y bar. Okay. I sub x bar, we already know it's bh cubed over 12. So bh cubed over 12 plus, now we have to solve for iy bar. Now iy bar, so that's this axis. So what we're gonna do now is take another element. Okay, so let me redraw. We have this. Okay, this is your xy, and then this is the centroid, so this is your x prime, and then this is your y prime. We're looking for a moment of inertia about the centroidal y-axis. And as I've said earlier, we're going to take an element parallel to your axis in question. So it's a vertical axis, so we take a vertical element. Okay. Taking a vertical element. And then this is now your dx. Differential thickness x. Okay, so this thickness is very small, similar to here. This thickness is very, very small. That's why it's dy. So this dx prime. Okay, and then the equation now is plus integral of the x. Our equation for moment of inertia about the x-axis. Okay, let's see. Sorry, about the y-axis. So x squared dy. Integral of x squared dy. Okay. So now, sorry, BA. So now, BA is this differential area, which we can write as base times height since it's a rectangle. Base is your dx prime. Height is this, which is equal to h. Right? This h over 2, h over 2, b over 2, b over 2. So this is just b, this is just h. Once again, differential area, here, area of your strip, base times height, dx times h. Okay. And similar to what I asked earlier, usually the next step is to find out the constants. Here our constant is h because no matter where you place your strip, the height of your strip is the same. It's consistent at h. So this becomes h. And then take your limits. Once again, this is your 0. If this is base, this is negative base over 2, then this is positive base over 2. Negative b over 2, positive b over 2. B over 2, positive b over 2. Then integral of x prime squared dx prime. Okay, so let's solve. So this now bh cubed over 12 plus this equation h integral of x squared dx from negative b over 2 to b over 2. Then solving for that, bh cubed over 12 plus integral of x squared dx is x cubed over 3. So h times x cubed over 3, h cubed, yeah, correct, x cubed over 3. And then evaluate from negative b over 2 to positive b over 2. Let me just move this. Positive b over 2. And like I did here, instead of integrating from negative to positive, let's just multiply it by 2, then integrate from 0 to positive. So bh cubed over 12 plus multiplying by 2, you get 2h. Then I'm going to factor out this 3. That's why this becomes 2h over 3. Then we're left with x cubed. And then evaluate from positive b over, from 0 to positive b over 2. Okay. So bh cubed over 12 plus 2h over 3. Subbing in our values here, it's positive b over 2. So b over 2 cubed. Okay, b over 2 cubed minus subbing in 0, so minus 0. Okay. So we're left with bh cubed over 12 plus twice hb cubed over 2 times 2 raised to 3 is 8. 24. So this becomes twice hb cubed over 24. And this simplifies to bh cubed over 12 plus, okay, simplifying this, it's hb cubed over 12. Then simplifying further, okay, so that's bh cubed plus hb cubed over 12. Factoring out or simplifying this, yes, correct, John? Okay. Both terms have 1 over 12 and both terms have h and b. So this becomes 1 over 12 bh, or bh over 12 multiplied by h cubed plus b cubed, b squared, h squared plus b squared. Okay, and that is your final answer. Okay, that's your number 1. Any questions for number 1? Please answer in the chat. Okay, since none, let's move on to number 2. And you may recite now, number 2, determine the moment of inertia with respect to the x-axis for the circular area shown in the figure. So this is your given x-axis. So now we're looking for moment of inertia about that. So once again, let me copy the figure. And then paste. Okay. Number 2, looking for moment of inertia about your x-axis. Now this x-axis actually passes through the centroid of your circle. As you can see here, this is your origin of this radius A. So it's at the center of your circle. So we're looking for centroidal moment of inertia again. So I export. And then our equation, call it y squared dA. So y squared dA. Okay? And then our axis in question is x. So next step is to take an element parallel to your axis. So it's this. Okay? Now from that element, I can take an equation for dA. So this becomes integral of y squared. Can anybody give me the new equation for dA? Very good, Angela. 2x multiplied by its height, which is dy. Okay, so how did it become 2x? Got it. Because, okay, base times height, right? Area of your rectangle. Okay, base is this length. Now, this is your circle. Therefore, we can say from this point, okay, from this point up to this point, that's your length x. Okay. However, we need the total length. And since this is a circle, it's symmetrical, therefore this is also x. So x and x, so that's 2x. And wherever you are in your circle, let's say we're here, okay, this length is still x, right? And then this is still x. And x is the equation or the x coordinate of your circle. So that's why it's 2x for the total base of your rectangle. And then height, since we're taking a horizontal strip, that's your dy, differential height y. That's why this dy. Okay, next step is to take your limits. So your upper and lower limit. Okay, so instead of a, let's say, so that it's easier to understand, this a is the radius of your circle, so a equals r. Okay, so knowing that this a equals r, radius of your circle, can anybody give me what is the lower limit of this equation? Correct, John and Angela, negative r. Negative r, why? If this is radius, your r, okay, and the lowest limit is here, therefore this point is negative r. Right? So negative r. And then likewise, upper limit is this point, and that coordinate is your positive r. Okay? So from negative r to positive r. Then let's solve. Now, as you can see, our differential is in terms of y, but I have an equation or a term in terms of x. So remember, for integrals, we need uniform variables. So now I need an equation for x in terms of y. And how do we get that? Well, considering this is a circle, I know the equation of a circle, right? That's r squared equals x squared plus y squared. Therefore, from this, I can say x is equal to square root of r squared minus y squared. I'll sub that here into this equation. We get integral of y squared times 2 square root of r squared minus y squared dy from negative r to r. Okay. Now don't worry, even though I have an an r there, r here is a constant. Why? Because that's the radius of your circle. No matter where you are or where you put this element, the radius of your circle is the same. That's why that's just a constant. Okay, so now I have that equation, integral of y squared times 2 square root of r squared minus y squared dy from negative r to r. Now this is just a matter of integral calculus or differential equation. So I'm not going to show that solution anymore since we're concerned with mechanics here. Okay, so I'll just note using differential equation. Okay, ix bar is actually equal to pi r raised to 4 over 4. Yeah. Okay. Don't worry, in your exam, I won't have you solve for these. Okay. This is just deriving equations for moment of inertia for simple shapes. If you haven't noticed, yeah, I'm just deriving equations of moment of inertia for simple shapes. Previously rectangle, now we have your circle. Okay, so that's your number 2. So now we have an equation for centroidal x-axis of a circle. Okay. Any questions for number 2? Please answer in the chat. Okay, since since you don't have any questions, let's move on to number 3. Okay, number 3. The rectangle is 3 inches, height 6 inches. Determine the polar moment of inertia and the radius of gyration with respect to a polar axis through one corner. Okay, so now we have values, it's not variables anymore. So let's solve. Polar moment of inertia of this rectangle, as well as radius of gyration. Okay, number 3. So recall, equation for polar moment of inertia is ix plus iy, or integral of r squared dA. Now using integral of r squared dA is for irregular shapes or for variables. Since this is just a rectangle and their dimensions are given, I can use the other equation, j equals ix plus iy. Okay, iy. So now the problem here is, what is ix and what is iy? Well, we've solved for this equation of moment of inertia of a rectangle. And to be more specific, this is about our x-axis, or sorry, here, about our x-axis and our y-axis. Okay, so about our base and about this height. We have an equation about the base, right? Let's see. Here. No, not that. Here. This is our moment of inertia about the base of our rectangle, right? It's bh cubed over 3. What's the same for here as well? So ix is bh cubed over 3. And then iy, okay, so to solve for iy, you don't have to go through the integral. So it's just the same. The variables are just split. So instead of bh cubed, it's now hb cubed. Because solving for iy is just basically rotating this. Okay? This now your y, this is your x. Your base now is h, this is your b. And then going through what we did earlier in integral calculus, or for integral calculus, we'll get the equation HB cubed over 3. Okay? So HB cubed over 3. Yeah. Okay. And then let's just sub in our variables. Base is 6. 6 times 3 cubed over 3 plus 3 times 6 cubed over 3. Please solve. What's the answer? Correct, Jan? Carla? So Torres, iba. Torres, isa pa lang. Torres. Iba. Okay. 270 plus. So 270. Now the question here is, what is the unit of polar moment of inertia? Unit of polar moment of inertia is the same as moment of inertia. If we look here, base times h cubed, all of these are in inches, so inches times inches cubed, that is inches to the 4, or inches raised to 4. So final answer, 270 inch raised to 4. Okay, so that's letter A. Next, letter B, radius of gyration. So K, we're looking for K. And remember, we have an equation for K, which is, hindi ba ikaw? Sorry. Oh, okay. Thank you, Bara. So not Carla. Thank you for letting me know. It was Andre Talavega. Thank you for your honesty, Andre. O sige, +2 daw sa honesty. Okay. I value honesty a lot, so I appreciate that. So, where was I? Radius of gyration. Let's look for an equation. These are our equations. However, the problem states we're taking radius of gyration by a polar axis. So this is the equation that we'll use. Integral of j over a. Okay? Integral of, integral. Square root of j over a. We know j, that's 240. Integral of 240. And then area is just the area of your shape, your figure. This is just a rectangle, so base times height, 6 times 3. Please solve. What's the answer? Correct. Jan and Kathleen. Cortades and Dupra. Right. 3.87. 270. Eh? Yeah, 270. 270. 270. Kamali lang. Right. Once again, it's 3.87. And then unit for this, for radius, it's just a radius. So one dimension, so that's just inches. Okay. So that is your numbers 2 and 3. Any questions for numbers 2 and 3? Please answer in the chat. Okay, since you don't have any questions, let's move on to number 4. Okay. Number 4. Okay. Right. So how to solve for number 4? So what we have here is a circle, and then this is an empty space. So essentially we have a ring. So to solve for that, it's the same concept as your centroid. We're just subtracting the empty spaces. Okay? What are you looking for? Number 4, determine the moment of inertia and radius of gyration with respect to a polar centroidal axis of the cross-section of a hollow tube whose outside diameter is 6 and inside diameter is 4. Therefore, outside radius is 3, inside radius is 2. So we're looking for moment of inertia and then K. So moment of inertia with respect to a polar centroidal axis. So that's essentially your polar moment of inertia, even though it's not specified here. Reading the whole problem, okay, about a polar axis, so that's polar moment of inertia. So we're looking for J, not I. And then equation for J, once again, about a centroidal axis is Ix plus Iy. Okay, now we've solved for moment of inertia of a circle, right? Let's see that here. And it's also about the centroid. So polar moment of inertia about x is pi raised to 4 over 4. Now this is symmetrical about x and about y. Therefore, moment of inertia over for a centroidal axis y is also pi r to the 4th over 4. So therefore, we're going to use this equation. Pi raised to 4 over 4. Pi r raised to 4 over 4. Now, again, we have two shapes here. One is an empty space. So if you have an empty space, you're just going to subtract. So the equation becomes for Ix, okay, so pi r raised to 4 over 4, and then let's specify that's your outside diameter for the total circle. Okay, so for the larger circle. And then subtract the empty space. So r there is 2 pi r, and then let's call that inner for inner radius raised to 4 over 4. Okay? Yeah. And then plus your Iy, and as I've said earlier, Iy is just the same as Ix, same equation. So pi r to the 4th over 4. Again, that's Ro, the 4th over 4, minus pi Ri. Okay, now let's just sub in the values. So pi Ro is 3. So pi times 3 raised to 4 over 4 minus pi times Ri is 2. So 2 raised to 4 over 4. And you can just multiply this by 2 since that's basically the same equation, or we can copy this. Pi Ro is 3 raised to 4th over 4. And then minus again, Ri is 2. Pi times 2 raised to 4 over 4. Please solve. What's the answer? In decimals, please. 65. Okay, correct Jermaine and Pauline. Tama ba? Yeah. So 65 over 2 pi, but since this is final answer, you can just write it in decimal. So Jermaine and Pauline, you're behind. Funny. ABCD. Okay, 102.10. And then again, unit, it's in inches, so inch raised to 4. Okay. Right. Next, we're looking for radius. So okay. And it's about, it's the same as also about your polar centroidal axis. So therefore, we're going to use equation J over A. Okay, so this is K sub O, so that it's polar radius. So J over A. So J, use the stored value of this over A. So area of your shaded region. So that's just area of a ring, and we know the area of a ring is just pi or outer squared minus inner squared. So 3 squared minus 2 squared, right? Your solid mensuration. Please solve what's the final answer. John and Adrian. So Relor and Rivera. Oh, Rivera. Okay. Correct, it's 2.55. And then unit, once again, this is just a radius, so inches. Right. That is your number 4. Any questions for number 4? Please answer in the chat. Okay, since you don't have any questions, let's move on to question number 5. Okay. Question 5, determine the moment of inertia for the shaded area shown in the figure about the x-axis. So just moment of inertia about the x-axis, so it's I sub x. So let's solve I sub x. Okay, let's solve. I sub x is equal to, our equation was y squared dA. Now the reason why I'm using integral is because we don't know what kind of shape this is, or actually this is a segment or a portion of a parabola. But since we don't know the equation for that, we're going to use integrals. So we're going to go back to integral of y squared dA. And then we're solving it about the x-axis. So next step is to take an element parallel to that. So that's why we have this. So base is this, height is dy. Okay, so rewriting our equation, this remains as y squared. Now let's create an equation for your differential area. Again, it's base times height. So the question here is, what is our base? How do I get this? Can anybody tell me what is the equation for this? Considering this line has the x and y coordinates of your equation, so how do I get this? In baseline, yeah. Correct, Eileen and Skylar, it's 100 minus x as well as Angela. There are 2 points can Angela. Correct, Skylar and Eileen. So pamatmat and Ortega. Pamat. Ano? Last chance na today. Okay, so it's 100 minus x. So bakit? Yeah, congrats. So this total length is 100. However, I want this. How do I get that? And recall, this line represents your x and y coordinates of your equation. So therefore, to get this, it's just 100 minus this length, which is the x coordinate of this point. So that's why it's 100 minus x. Okay, once again, total length 100. Subtract this from 100 to get this base. And this is just the x coordinate of your curve. This is your curve. So 100 minus x. And then height, dy. And then now let's get the limits. Lower and upper limit. Considering this is your x, therefore this is your 0. So can anybody tell me what's the lower limit? Here. Lower limit of our integral. Correct. Correct, Jan and John. Kenya Torres. Torres, naka 2 points ka na ba? Yeah. So the next one, DeAndre. Ba yan? Age 0. Correct, John. It's 0 to 200. Or lower. So 0 up to 200. Why? Well, it's already given. Base is 100. Total height is 200. Therefore, our limit is from 0 to 200. Okay. So now I have an inconsistency in our variables. My equation is in dy. I have an x here. So I have to change that. So to change that, look at your figure. This is where we took our x. And this curve has the equation y squared equals 400x. So I can make an equation for x in terms of y out of this. So now we have x equals y squared over 400. Yes, correct. So I'm going to sub that here, integral from 0 to 200, y squared 100 minus y squared over 400 dy. Now, the great thing about solving for this is you can just use your calculator, right? If you know the integral function of your calculator, you can solve for this. So once again, try to study your calculator so that your solution is shorter. So please solve. What is the answer here? Okay, very good. Skylar and Shanine. So Pamatmat and Santa Ana. Santa Ana. So it's 106.67 to be more specific, or 107 times 10 raised to 6. Okay, so we'll use the more specific one. 106.67 times 10 raised to 6. And then our unit is in millimeters. This moment of inertia, so millimeter raised to 4. Okay, so that's our answer. Now there's another way to solve for this, and I'm just gonna show you. And that is, instead of taking a horizontal element, I'm gonna take a vertical element. So what's gonna happen if I do that? Well, you'll find out that it gives me a more complicated solution. Okay. So there, this is 100, 0, 100, 200, and then we'll take a vertical element. What's gonna happen there? So what happens here is, okay, now our element, or the portions of our element, is, or the distance of the portions of our element is not consistent or constant to your x-axis. Okay? Meaning, for example here, no matter where I take my point, okay, recall this is a very thin strip. Okay? So generally I can only get these portions. All of these portions are the same distance from the x-axis. So that's why I can just take it as a whole. However, here, for this strip, okay, taking different portions of that strip, all of them have different distances from the x-axis. So that's why it is better to take an element parallel, or a strip parallel to your axis in question. Because again, you'll get something like this. So you can still solve for this. Now, we're gonna use another technique. Okay, so recall, whenever we're solving for example here, okay, I'm gonna take moment of inertia of this point about this axis. Okay, but I know the moment of inertia of its centroid to this axis. So I'm actually taking moment of inertia from a parallel axis. And from that, we can take your parallel axis theorem. Recall, parallel axis theorem is just ix bar plus aby squared. Okay. But again, this is the general equation. What we're gonna do is take small elements of each. Okay. So we're gonna take the differential moment of inertia of each element. So this becomes differential inertia x equals, again, differential inertia or centroidal inertia plus differential area. Okay, and then dy squared. So that it's not confusing, let's call dy y prime. Okay, this is y prime. Distance of your portion of an element to your x-axis. So dA times y prime squared. Okay, now let's just solve. We know the centroidal moment of inertia of a rectangle. Okay, again, the technique here is we're dividing this area into very small shapes, or into very small squares or rectangles. Okay, and then adding all that up to get the total moment of inertia. So therefore, this differential inertia is that of a rectangle. Okay, and recall, we know the centroidal moment of inertia as bh cubed over 12 for a rectangle, right? Centroidal moment is this bh cubed over 12. So let's copy that. So bh cubed over 12, b of our rectangle, so this is a vertical element, this is dx. So b is dx, and then our height, the height of our rectangle is this. Okay? And that height is from 0 up to this y coordinate. Therefore, yes, correct, John, it's y. And over the cube over 12. Okay, so dxy cube over 12 plus, next taking the area, this differential area, it's dx times y, right? We've established that. Dx times y, and then y prime. So how do we get y prime? So y prime now is from this point to this point, and this point is the centroid of your element. Centroid of your element of a rectangle. So therefore, it just divides your length or your measurements to 2. If this total height is y, therefore this is height, y over 2. Here. But y over 2. Okay, y prime equals y over 2. Again, y prime is just distance from centroid of your element to your reference axis. So y over 2. And then simplifying that squared. The xy cubed over 12 plus dx times y over 2 squared. All of this simplifies to 1/3 y cubed dx. Okay, so that's the moment of inertia of a strip. So our goal is to take the moment of inertia of everything. So to do that, just take the integral of it. So integral of 1/3 y cubed dx, and then take our limit. Okay, this is a vertical strip, so our limit are from this point to this point. So from 0 to total base 100. So 0 to 100. And once again, this is in y, this is in x. So therefore, I need to rewrite this in terms of x. So 0 to 100, 1/3. So I need an equation of y in terms of x. We have this equation, y squared equals 400x. Therefore, y is square root of 400x. So this is now square root of 400x cubed dx. Okay. And then if you solve for this, you should also get your 106.10.67 times 10 raised to 6. Yes, very good. Times 10 raised to 6, and once again, the limiter raised to 4. Right, so that's your solution. And then from the two solutions, one is significantly easier than the other. Okay, so that's why I keep telling take the element parallel to your axis in question. And that is number 5. Any questions for number 5? Please answer in the chat. All right. Since you don't have any questions, the next topic is moment of inertia for composite areas. Okay. However, it's already 1:30, so I'm gonna let you have your break. Okay, I imagine you want a longer break, so let's continue our lecture at 2 o'clock. Okay? So have your break, eat your lunch or nap. Just come back at 2 o'clock. Okay? And you may go. See you later. Okay. So we're down to our last topic. We answered the final problem for the previous topic. Now let's move on to moments of inertia for composite areas. So a composite area, you already know this, a combination of areas. It consists of a series of connected simpler parts or shapes, such as rectangles, triangles, and circles. So provided the moment of inertia of each of these parts is known, or can be determined about a common axis, then the moment of inertia for the composite area about this axis equals the algebraic sum of the moments of inertia of all of its parts. So algebraic sum means for shaded areas, it's positive. For empty spaces, it's negative. Same with your centroids and center of gravity. So here are our equations, moment of inertia and radius of gyration for simple shapes or common shapes. First is your rectangle. We already solved for this. Ix bar centroidal moment of inertia is bh cubed over 12. Then about its base, your x, it's just bh cubed over 3. Radius of gyration, kx, is h over square root of 12 about the centroidal axis. And then it's h over square root of 3 over by the base. So take note here, x is your reference axis, x prime is a centroidal axis. So for a triangle, our equation now is for centroidal moment of inertia, bh cubed over 36, while your moment of inertia about the base of your triangle is bh cubed over 12. And these are the equations for centroidal and then about the base. So these equations are taken by using the integral of rho squared dA, like what we did earlier. Likewise, for your circle, we've already solved for this. Centroidal is pi raised to 4, pi r raised to 4 over 4. And then, instead of moment of inertia about a reference axis, we have a polar moment of inertia. It's pi r raised to 4 over 2. Okay, and then moment of inertia about your centroidal x-axis and moment of inertia about your radius of gyration about your centroidal x-axis, this radius of gyration about your z-axis or about your pole O, hence K sub O. Next, we have a semicircle. Okay, here, Ix, moment of inertia about your base x is equal to moment of inertia about the centroidal y-axis. This is your y prime. And it's pi r raised to 4 over 8. And then moment of inertia about the centroidal x-axis here is 0.11 r raised to 4. Radius of gyration about your base x-axis and about centroidal y-axis is r over 2. And here centroidal x-axis is 0.264 r. Next, for your quarter circle, Ix equals Iy. So base x, moment of inertia about base x and base y is the same, pi r raised to 4 over 16. And centroidal moment of inertia about x prime and y prime is the same, it's 0.055 r raised to 4. Moment of inertia about base x and height y, okay, here x and y is the same, r over 2. Likewise, centroidal moment of inertia about x and y, or x prime and y prime, is 0.264 r. And then lastly, you have an ellipse. This is an ellipse. Moment of inertia about centroidal x-axis is pi ab cubed over 4. A is half the length of your major axis, so from center to vertex. Okay, and B is the half the length of your minor axis from center to your co-vertex. So here your B. And then centroidal, a moment of inertia about centroidal y-axis, similar to your rectangle, you're just gonna transfer your variable. So instead of pi ab cubed, it's now pi ba cubed over 4. And then your radius of gyration about your centroidal x is b over 2, and then about centroidal y is a over 2. So here is basically just using these equations depending on what's being asked in the problem. Okay? So for us to understand this better, let's have a few examples. Okay, let's start with number 1. Again, ready your calculator. You're gonna take recitation. Determine the moment of inertia of the area shown in the figure about the x-axis. Right. So here, we have a rectangle, and then we have an empty space in the form of a circle. So let's solve for that. So like I've said earlier, whenever you have an empty space, you just subtract. So the goal here is to get the moment of inertia of your rectangle and your circle. Let's start with the rectangle. Okay. Moment of inertia about the x-axis. Let's call that IXR. And we already know the equation for this, right? It's BH cubed over 3. If it's about the base, BH cubed over 3. Then let's look, base of our rectangle is 100. Height is 75 plus 75, 150 cube. And then base, over 3. Please solve. What's the answer? Okay, correct, Joanna and Jade, and John and Jan. But John and Jan both have 2 points already, I believe. So I'll give it to Christine and Jade. So tamanos mo. Just so more people have chances. Okay. Yeah. 100 times 150 cube over 3. So it's 11.25. We can rewrite it this way, times 10 raised to 7. Okay. So store that in your calculator so that it's easier to retrieve. Okay, next, let's solve for your circle. Okay, so for your circle, let's see. This is our axis in question. This is your circle. So the axis of your circle is not on here. So we're going to use parallel axis theorem, since the only equation that we know is moment of inertia about the centroid of this. So using parallel axis theorem, let's call this IXC for the circle. So the equation for that is centroidal moment of inertia plus AD squared. ADY squared. So centroidal moment of inertia, recall it's pi r raised to 4 over 4. So pi r raised to 4 over 4 plus a area here of our circle is pi r squared. So pi r squared and then dy squared. Next, let's plug in our values. Pi r is given. Okay, r is given. It's here. It's 25. So pi times 25 raised to 4 over 4 plus 5. Again, r is 25 squared dy squared. And this dy is the vertical distance of your reference axis from your centroidal axis, from your axis in question. So this axis in question, centroidal axis, distance between them is 75. So 75 squared. Please solve. What's the answer? Oh, what happened? So 110. Okay, I know where you got wrong. Okay, some of you did square, okay, instead of raised to 4. So then kind of common. Okay, so it's 11.35. By the way, you can just write in scientific quotation if you want, since the answer is very large. So who wrote 11.35? Andre and Jermaine. So De La Vega and Bordet. De La Vega. 11.35 times 10 raised to 1, 2, 3, 4, 5, 6. Okay. Again, store, since this is pretty long. Okay, and then to solve for this, to get the final answer I, x, okay, just take your shaded region subtracted by your empty space. So, okay, xr minus I xc, you stored both values, so this should be easy. What's the final answer? Correct, Hailey and Vivian. So Ortega, Bao. Okay. Vivian. Ortega. Okay. So, scientific notation, we can just write 101.15 times 10 raised to 6. Then unit, our unit is in millimeters. This is moment of inertia, so millimeter raised to 4. Okay, so that's your number 1. Any questions for number 1? Please answer in the chat. Okay, since no questions, let's move on to question number 2. Okay. Determine the moments of inertia for the cross-sectional area of the member shown in the figure about the x and y centroidal axis. So we're looking for 2 things, moment of inertia about x and moment of inertia about y centroidal axis. Okay, let's solve. Okay. So cross-sectional area, I just need to get a cross-section of this. And it looks something like this. Right? So that's the cross-section of this. Habaan natin. Okay. So we have 3 rectangles. Now it's up to us how to divide this into common shapes. So for me, I'm gonna divide it this way. So this is my area A, area B, area C. Okay. A, B, C. So now what we're gonna do, we're like taking moment of inertia about x and y. So we're gonna take moment of inertia of each segments about x and y as well. Okay? And then the centroidal axis is here, this is your C. This is your X centroidal axis, and then this is your Y centroidal axis. Okay? Let's try making this larger. Okay. So let's start. You can start with whatever segment. For me, I want to start at B because the centroid of B is directly at the centroid of this axis as well. So using B, let's start with moment about x-axis. Okay. So moment of B about the x-axis and your x-axis is at the centroid. So therefore, I need the equation for moment of inertia about the centroidal axis of a rectangle. And the equation for that is BH cubed over 12, right? So you can use that. It's BH cubed over 12. And then let's solve. Base of this, looking here, okay, the total width is 600. So 600 times height. Let's look at the height. It's given here, 100 meters. So 100 cubed over 12. Please solve. What's the answer? Again, you can use scientific notation. Mm -hmm. Correct, Eiley and Pauline. So Eiley already have 2 points. I'll give it to Connie and Deluyo. Connie. Deluyo. Okay. So it's 5 times 10 raised to 7. Or 50 times 10 raised to 6. 5 times 10 raised to 7. So that's for IX for your B. Next, let's solve for IY. And recall, for IY, it's just HB cubed. Okay. Nauna si Pauline and Sophia sa'yo. Kaya sila muna. Okay. Again, for IY, it's just HB cubed over 12. HB cubed over 12. So H is 100 times 600 cubed over 12. Please solve. What's the answer? Correct, Jan, Julia, and Joanna. So Tamano, Solomon. Solomon, Tamano. Okay, 2 points. So correct, 1.8 times 10 raised to 9. Okay. So now that's your IX and IY. Put that to the side. Now we need to solve for A and C, block A and C. But take note, okay, A and C have the same area, right? They're both has a width of 100 and has a height of 400, and they're both oriented the same way. And not only that, their centroids are both are equidistant from your axis. In short, they're a bit similar. Okay, so that means I can just solve for IX and IY them both. So A and C. So let's start again with IX. Whether you analyze A or C, you're gonna get the same answer. Let's try analyzing A. So centroid of A is here. Okay, that's the centroid of that. And it's not on the centroidal axis. Therefore, I need your parallel axis theorem. And parallel axis theorem is centroidal axis plus AD squared. Okay, so centroidal axis, once again, this is a rectangle about the x-axis, so that is BH cubed over 12 plus area of your rectangle BH. And then distance squared y squared. Now let's compute. B, base of this green rectangle is 100. height of it is, if this total thing is 400, right? And then this is 100. Therefore, the remaining area now is 300. So therefore, height of that is 300. 300 cube over 12. Then base times height. Again, base is 100. Height is 300. And now we need to get the distance. So let's see, what is that distance? It's this value. Oh, here. It's this. Okay? Or it's also the same as this. You can say this. Okay? So it's the same distance. So to compute, again, total length of this is 400. So what we're left here is 300, right? Okay. So therefore, the center of that, this would be 150. Since total length is 100. This is 150. Okay. And then this total height is 100. Therefore, the remaining length is 50. Therefore, total length of this is 200. So that's why this is 200 squared. Please compute. What's the answer? Correct, Irie and Shanine. Joso and Sankar. 50 points. It's 1.425 times 10 raised to 9. Okay, once again, store that. Same thing here. Store. Okay. Yeah, squared. Yeah. Okay. So this is the same for A and C. Once again, because they have the same area and they are the same distance, or their centroids are the same distance from your x-axis, which is also 200. Okay, now let's go with IY. Okay, so for IY, same thing. Its y-axis is not lying on the reference y-axis. So using parallel axis theorem, this I bar y plus a px squared. Centroidal moment of inertia about the x-axis, or rather about the y-axis, is hb cubed over 12. Then area is still bh, or hb if you prefer that, and then bx squared. Okay, let's plug in our values. Height is 300. So 300 times 100 cubed over 12 plus area. That's 100 times 300. But now we need to get this distance. Okay? So from this to this. Okay, so how do we get that? Let's look here. This total length is 600. Okay? So therefore, if this is 600, thickness of this bar is 100. So half of that is 50. So we just get 300 minus 50. So this is 250. Okay, you follow? Once again, total length is 300, half of that. Therefore, this is 300. Minus half the length of your bar. So that's minus 50. 300 minus 50, that's 250. Therefore, this is 250 squared. Please solve. What's the answer? Correct, Vivian and Adrian. Rivera and Vivian. 2 points. 2 points. Right. 1.9 times 10 raised to 9. Okay, so 1.9 times 10 raised to 9. Once again, store. Alright, so now you've successfully solved for Ix and Iy of every segment of your figure. So now getting the final answer. Therefore, Ix, total Ix of everything is just a summation of your Ix. So your Ixa plus Ixb and Ixc. So solving for that. Okay. So 5 times 10 raised to 7 plus. Okay. Since Ix of A and C are the same, I can just multiply it by 2, okay? So twice 1.425 times 10 raised to 9. Please solve. What's the final answer for Ix? Correct, Carlo and Rovi. 3 Kenyan pulses. Okay. Pulses. Right. 2.9 times 10 raised to 9. Good. So final answer here is 2.90 or 2.9 times 10 raised to 9. And now let's put our unit millimeter. Therefore, this is millimeter raised to 4. Okay. Do the same thing for Iy. Okay. Iy. Summation of Iy. So let's see here. This is 1.8. 1.8 times 10 raised to 9 plus, again, Iy of A and C are the same, so I'm gonna multiply it by 2, so 1.9 times 10 raised to 9. What's the total answer? Who got it first? Correct. Vivian, Ivy. Nakato ka na ba, Ivy? Joseph. Hindi pa. Okay, Ivy. And Kylie. 2 points ka na. Ortega. Yep. And then who else? Adrian. Yep. Janine. Vera. Santa Ana. Amita. Amita. Okay. And then Vivian on the second point. 3 points. Okay. O, yung mga wala pang recitation, is your chance. The final answer, 5.6 times 10 raised to 9. Again, unit is millimeter raised to 9. Okay, that's your final answer for Iy. That's it for number 2. Any questions for number 2? Please answer in the chat. Okay, since you don't have any questions, let's move on to the second to the last item for this term. Question number 3. Okay. Determine the moment of inertia of the T-section shown in the figure with respect to its centroidal X sub O axis. Okay. Let's start. Now the problem here is I don't know where that X sub O axis is. So I have to solve for that. So I have to solve for the centroid. Okay, and we already know how to do that, right? From our last topic, first step in solving for centroid is divided into 2 shapes. So this is your shape 1. This is your shape 2. Okay. This is A1. This is A2. So let's start A1. That's just a rectangle. So base times height. 8 times 2, 16. Okay. And then Same thing with number area 2. Area 2 base is 2, height is 8 given, so that's 16, and then total area 32. Okay, and then from that I can solve for either x bar or y bar. Now we want to solve for y bar because that dictates our distances from the centroidal x-axis. Okay, a y bar equals summation of a y. Okay, let's start. A1. Okay, our reference axis is this. Therefore, let's take those distances. Let's start with 1. Okay, this is the centroid, right? And this is your y1. Therefore, y1, as you can see, total height of this is 2. Y1 is half of that, so that's 1. Okay? And then, next, plus. Okay, plus A2. Both of them are above the x-axis or reference x-axis, so they're both positive. A2 has this distance, so this is the centroid of A2. Therefore, this is y3. Let's move this. Okay. This is your y2. And how do we get that? So this is half of 8, so this is 4. And plus 2, so that's 6. So y2 is equal to 6. Knowing that a is 32, please solve what's y bar. Correct, it's 3.5. Correct, Jan? Gladys. Then who else? Correct, Philip, Pamitan. Oh yeah, 2.7. Okay, it's 3.5. Right. So now I know that's 3.5. So that this axis is where I'm gonna take my moment of inertia. So let's solve moment of inertia about your x sub o axis. Okay. So as you can see, both of them don't have their axis about the centroidal axis. So both of them would require your parallel axis theorem. Now we don't have to separate it like what we did earlier. We can just write it all in one long equation. Okay. Whichever is more convenient for you, let's try that one long equation. So let's try ix bar plus a dy squared, and this is for your rectangle 1. Okay, so this just means for 1. Okay. You'll see this symbol a lot, especially for strength of materials. You'll see something like this, PL over AE, and then ST. This means equation for your steel material. Okay. Just so that you don't get confused. So this just means equation for my bar 1. And then plus, again, centroidal moment of inertia plus AD y squared. And this is about, or for the second bar, or second area. And now let's just create our equation. These are both rectangles, so this is BH cubed over 12 plus BH times D y squared for 1 plus BH cubed over 12 plus BH dy squared for 2. So now the question is, what are those values? So for 1, base is 8 inches, so 8 times height is 2. So 2 cubed over 12 plus area. So base times height, 8 times 2. And now this is where we need to analyze what is this dy. Let's solve for dy now. Okay, so dy is distance of reference axis to centroidal axis, right? So therefore, okay, this is the reference, or rather, this is the axis in question. And now that is your reference axis, and this is your centroidal axis. So this is your dy1, dy2, dy2, and then for dy1, it's this. dy1. Okay, dy1 is what we're looking for. How do I get this? So recall, this total height is 3.5. So 3.5 minus this, that is half the height. Height is 2, so 3.5 minus 1 squared. Yeah. Okay. Now let's go to the other equation plus. Okay. Base of this, your second area, 2. Height is 8, so 2 times 8 cube over 12 plus area, base times height, so 2 times 8, and now dy2. So here. So let's solve. Okay. Nasa dy2 pa lang ako. Okay. So dy2, how do we get that? Let's take this total height. Okay. So this is 4, this is 2, right? So total of that is 6. And then to get dy2, I'm just going to subtract your y bar. So 6 minus your 3.5. Now, and solve. Type in your answer. Okay, so Jan, correct. Shanine, correct. And Samantha, correct. Torres, Santa Ana, Dupra, correct, Kathleen. So Dupra, G. Okay, 290.67. Unit, inches, so inch raised to 4. Okay, so that's our answer. And that is number 3. Okay, any questions for number 3? Please answer in the chat. Okay, since you don't have any questions, let's move on to the last topic for this term, or last example of this term. Number 4. Find the moment of inertia about the indicated x-axis for the shaded area shown in the figure. Okay. So we have another empty space. We have a rectangle and your semicircle. So same thing as we did earlier, let's get the moment of inertia of each and then subtract the empty space. So let's start with the rectangle. Okay, we're taking moment of inertia about a base, your x-axis. So therefore, our equation is bh cubed over 3. Okay, base of that, solve. Radius of your semicircle is 4. Therefore, diameter is 8, which is also the base of your rectangle. So this is 8. Then times height is given 10 cubed over 3. Please solve. What's the answer? Okay, correct. Jan, Ailey, Samantha, soportados. 2 points. 2 points ka na din. Vivian, 2 points ka na rin. DeAndre, correct. 2 points na. Alright. So it's 2,666.67 and then store that. Next, for your circle, rather semicircle. Okay, so as you can see, centroid of your semicircle is not on the reference axis, so I need to use parallel axis theorem. So Ix equals Ix bar plus AB squared. So now I have to know what is Ix bar for a semicircle. So let's look at our equations. Ix bar is 0.11 r raised to 4. And make sure the orientation in the given table is the same as your example. So yes, then diameter on the horizontal. Therefore, 0.11 r raised to 4. So 0.11 r raised to 4 plus a. So that's just 1/2 pi r squared. And then d y squared. Okay, let's plug in our values. 1/2, 0.11. Radius is 4. So 4 raised to 4 plus 1/2 pi 4 squared. And now I have to know what's dy. So let's see. The centroid of a semicircle is somewhere here. And then this is your dy. Distance y. So the problem here, how am I going to get that? So let's see. Okay, recall from your topic from centroids, right? For a semicircle, even for a quarter circle, the distance of the centroid from the flat edge is 4r over 3 pi. Okay, remember? This is 4r over 3 pi. Therefore, dy is this total height minus that. So therefore, this is 10 minus 4. R again is 4. 4r over 3 pi. Okay? Please solve. What's the final answer? Sorry. Yeah. Correct. 176. Correct. Wala pang points. Sana? Okay. Oh. Sino bang 1 point pala? 7, 6, 7, 3. Okay. Okay. So correct pulses, Rovi. And then I'm gonna give it also to Vincent, since it's the first one. Okay, Cortades and pulses. Cortades. Wait, 6. Okay. So correct 1760.53. And now finally, to get Ix, it's just, okay, let's call this Ixr and Ixs for semicircle. So Ixr minus Ixs. Please solve. What's the final answer? Wala pang points. Correct, Kathleen, Vincent, Patricia. Correct. So Cruz. And then who else? Sophia De Leon. Okay, that's it. Final answer is 906.14. Unit, our unit is in inches, so inches raised to 4. That is our number. Any questions for number 4? Please answer in the chat. Naka-square pala to. How about the others? Please answer. This is the final. Do you have any questions for this term? So, last chance to answer na din sa Zoom. Yes, may Coursera kayo this module. Because this is the last lecture day. Okay? I'm gonna make your week 11 available. So deadline for your Coursera is on Friday, deadline. Okay, so Coursera week 5 and 6. Deadline next week, Friday. So, kasali pa rin siya sa grading natin. I'm gonna check if everyone has submitted their seat work number 3. And then I'm gonna upload the solution. Okay, later. I have to check it first. And then, okay, so this is our last lecture day. This is the last topic for MEC 30. Now, on Tuesday is your modular exam 3. Coverage is centroid and moment of inertia. Okay, so that's for Tuesday. So if you've submitted your Coursera by Tuesday and your modular exam, you can know your module grade or your module 3 grade. So week 5 lang ba yung Coursera? Di week 5 lang yung Coursera for module 3. Wait lang. Yung MG2 na nakikita nyo, hindi pa yun yung final grade. May extra credit pa. So yung final grade nyo is M2 grade. M2 grade. And di ko pa na-check yung mga late submission. So, wait lang. Hindi pa yan yung final. Yung mga late submission, checkan ko pa. Okay, again, M2 grade, yung final grade. Yes, I'm gonna manually check those late submissions later as well. Yes, IP exam is for those who had an IP for Module 1. Those who failed Module 2 or had an IP for Module 2, I'm gonna upload your IP exam this Sunday. Okay, so again, IP exam number 2 will be available on Sunday for those who got an IP. Because I have to check the late submissions. Okay, any other questions? Again, have to check late submissions and then IP exam on Sunday for those who got an IP. Your final grade is named M2 grade. Any other concerns? So here's the thing, for module 3, there shouldn't be completion or remedial because it's the final module. Okay, so I'm still thinking if I'm gonna give you an exam on Saturday. I'm still thinking. Okay, so I'm gonna give those who failed module 3 a chance to pass. I'll probably make an announcement about that. Okay, we'll see your results for module exam number 3 if I have to make a remedial exam. Okay, I'm gonna announce on Tuesday as well. And then there's no passing score for an IP exam. What you need to do is you need to answer it repeatedly again and again until you get a score high enough that your module 1 grade for IP students is above 70 or 70 and above. Okay, so it's in your grade center. Check your M3 grade, M1 grade, M2 grade for IP students. That is the updated grade after answering your remedial exam or IP exam. Okay, so there's no passing for IP exam. What's important is you get a score high enough to make your final grade 70. Can you guys check hanggang week 5 lang ba yung Coursera natin? Or is there a week 6?
Hanggang week 5 lang, ma'am.
Okay, thank you. So yeah, hanggang week 5 lang. Ayan. So week 5, for Module 3. Right? Now, any other concerns? So on Thursday, we still have a meeting on Thursday. Okay. So probably Thursday might be your remedial exam, if any, if there is. Or I'm gonna have you have your quiz show. Since we weren't able to have quiz show for Module 2 since we were out of time. So I was hoping we would get quiz show for Module 3 on Thursday. So that's our schedule. Tuesday, Module 3 exam, Modular Exam 3. Thursday, either IP exam for those who got an IP for Module 3 or quiz show. Once again, your points for your quiz show goes directly into plus points for your final grade in each module. Okay? I think that's it. Any other concerns before I dismiss you? Or, okay na? Okay, since you don't have any more questions, you may go. Goodbye, class.
Bye, ma'am. Thank you po.
Thank you po, ma'am.
Thank you, ma'am.
Po, ma'am.
Okay, wait lang. Saman, wait, may nagtanong. Ano, excuse letters are only for those who were significantly late in passing their quiz, like 10 minutes late. Okay? Okay.